Okay, everybody hear me? Everybody hear me okay? Okay, how about now? Yeah, seems like that's there. All right, so I'm Zach Brown. I work for Microsoft as a senior software engineer on the Office 365 security team. It's my job and my team's job to protect the data that's uploaded into OneDrive and SharePoint Online from hackers. So specifically, we spend most of our time on the data center side. We don't spend as much time on the front end side. So I'm looking at the actual computers, whether it's the machines running SharePoint Online or it's the Azure VMs supporting those services. My specialty on the team is I focus on host-based detection and large-scale forensic tooling. So I came from the Windows team originally, and so I like doing OS things. And then for large-scale forensic tooling, my time is spent trying to figure out how to take forensic data from 300,000 machines in a timely manner. So we'll start with a story. It's probably relatively familiar to blue teamers, and it's certainly familiar to red teamers who have caused this problem. It's not going to be very long, but it's going to kind of frame how we think about the rest of the talk. So this is a snapshot of a 4688 event. It's the process start event for those not familiar. That first highlighted line says that bad.exe was executed from system 32. Well, there's no bad.exe in the Windows build. That second line is the parent process, in this case w3wp.exe. That's a little weird. You don't really want w3wp.exe spawning new processes, so that's kind of concerning. We saw bad.exe run for a couple hours, and then when we go and we look for bad.exe on the machine, we don't find it. It's not there, and let's assume that there was no way to recover it, whether it was through deletion or whatever they've done. They've covered their tracks. So without the binary, it's actually kind of difficult for us to determine what might have happened at runtime, short of some artifacts that may have been generated. But we could probably get even better than what we have available to us just beyond the shim cache and the app-compat cache and things like that. So if we made a wish list, what would that be, right? Like, what would we want to know about a process that was running to see whether, to answer the question, yes, no, we need to freak out and start incident response. And so starting with networking, it'd be really nice to know what DNS lookups it performed, what IP addresses it connected to, how much data it transmitted to those IP addresses, and whether or not it was beaconing, right, talking to a C2. On the more behavioral side, it's really interesting to know what DLLs it loaded, right? Did it load the PowerShell automation DLL? Did it create threads in other processes? What WMI operations it performed, and whether or not PowerShell functions were called by that process, whether through injection or not. What if I told you it was all in the machine already, right? Like the logging is there. It's been there since Windows 2000. So ETW stands for Event Tracing for Windows. It's been publicly available since Windows 2000, but I think it actually goes back to the early days of NT. It's originally for debug scenarios, and so teams would use it for things like performance traces to figure out how much battery drain you're getting, and you'd use it for power management performance for like speed of API calls performance, and then power management for battery drain scenarios, CLR behaviors for things like when is garbage collection happening, when are we allocating memory, and then tracing of various subsystems. And actually various really should be most. There are a ton of providers available. There's two major categories of providers, and we're going to only spend time on user trace providers. Kernel trace providers are special, and they're not special necessarily in a way that matters, because a lot of the data that's available in a kernel trace provider is also available in a user trace provider. Just in the user trace providers alone, you've got over 1,100 on Windows 10. And this ranges from stuff like PowerShell to WinINet to WinRM, which is PowerShell remoting. DNS, RDP, firewall, the list goes on and on and on. Excuse me. That command at the bottom there, logman query providers, pipe to providers.txt, that if you run that on any machine, certainly Win 7 and above, I'm not sure, you could probably go down to Windows 2000 and above to do it. And that tells you every provider that's available on that machine right now. So what is ETW? I'm going to talk a little bit about how it works, and then we're going to do some demos, which hopefully will kind of show you how the code's written on that. So every component, and so component, when I say component, I mean system.management.automation.dll, so PowerShell, or wininet.dll. They all have the ability to register to expose a provider. So typically each component, so each DLL only exposes one provider. The providers, the green box is in there for people sitting in the back, and the purple box is the actual component itself. A consumer says, hey, I want to listen to the PowerShell provider. And so they create a trace session, and that trace session is responsible for subscribing to those providers. After that, the consumer sets up a callback that allows you to process the messages or events that are coming out of these providers. So you've got your message that component A generated, goes through the trace session, invoked on the callback. Consumer processes the data, returns control to the trace session. Some interesting things here. A provider can expose one or more types of events, and events are schematized. The quality of the schematization across providers is very variable. For example, in PowerShell, the most useful data comes from a well-formatted ginormous string blob, whereas in wininet, they give you a pretty specific breakdown of each event. So it just depends on how the provider creator has actually decided to schematize it. So what does an event look like? And don't worry, you're not supposed to be able to read that. This is just an overview snapshot of Microsoft Message Analyzer. It's a tool that my team uses to investigate ETW and spend time looking at it. I'm going to have a link at the end for where to get it. But this is kind of our exploratory tool when we want to understand what data is exposed by new providers. We'll load up Microsoft Message Analyzer, turn on the trace, and do some weird stuff and see if it actually generates signals we think are interesting. So this is, I've zoomed in a little bit on that center part. And that highlighted line says command invoke mimikatz is started. So this is that trace was from the PowerShell trace. So I went and made a fake invoke mimikatz and I ran it. And this is one of the events that came out of the PowerShell trace. And when we drill down, on the bottom portion of the PowerShell of that window, the top left there is the available properties. There's 4 in this case: context info, user data, and payload. The highlighted one, payload, gives you kind of a summary for the PowerShell provider in this case. And then every event that comes through ETW actually has a common header, and that header has things like timestamp, process ID, which is the process ID that generated that event, and the thread ID that for the thread that generated the event. And then on the right here, I've expanded the context info property. Now this is the property I was talking about where PowerShell gives us this big, nicely formatted string back. That's what this is. So on the far right side there, you can see that first highlighted line says host application. And that's whatever application loaded PowerShell.exe, or not PowerShell.exe, sorry, system.management.automation.dll. So if you were to use PS attack or not PowerShell, you would see the path to that file instead there, instead of PowerShell.exe. That second line is again the command that we were talking about, and the third line is the user who executed it. So it's my user in this case. There's another line I didn't highlight because it's empty right now. It says script name. If for whatever reason your attacker had decided to drop a script on box that was calling invoke mimikatz directly, you'd get a path to that script. So you can imagine if you're consuming this in real time in some sort of agent model, you can say, oh, hey, I see that the script name is not blank. I'm going to go grab that script and archive it for later use or investigation. Now, imagine like being able to get some of this sort of data into your SIM, right? This is pretty handy stuff. It's not easily exposed right now through the event log, the Windows event log, and there's not a lot of basic ways to consume it. So how do you actually capture it, right? We've got two main categories. I'm going to go over both, but we're only going to focus on one. We start with log files. This is the traditional kind of developer model when Windows uses it for diagnostic logging. So what you do is you take xperf or you take logman.exe and you turn on some traces, and it generates an ETL file. And that ETL file is something that we can go and load into Windows Performance Analyzer. There's a couple of other visualization tools that can break apart ETL files to show you timings and events that have occurred. So you can see things like, oh, I traced the lifetime of this managed application and I saw it garbage collect here and here and here. It doesn't solve the problem of volume though. For example, I mentioned a little bit earlier that performance power management traces in Windows. When I was working in Windows, we'd use those. So what we would do is we'd set up some scenario. We would turn on the tracing. We'd put the laptop to sleep. We'd let it sleep for 20 minutes, and we'd turn it back on, or open it back up, basically. And then we'd stop the trace and collect it. Well, that trace with just power management and some other basic stuff was 15 gigs. That's 20 minutes worth of data. You say, okay, fine. I'll do it, and then I'll parse it on box and filter out and pipe the events I actually want. Well, if you think about that, if you're generating 15 gigabytes in 30 minutes, and you got 1,000 endpoints, and you want to take all of that processing power, and especially if your endpoints are not just servers that have extra CPUs to be spinning, which I'm betting most of your servers don't, it's just not tenable, right? It never scales. On the other hand, we can do real-time processing, which is writing the custom code that actually handles these events as they come in. So you register for your provider, like the example I showed earlier, and you say, oh, hey, I want event ID 11, 12, and 13, but I don't care about the other 35 that this particular provider generates because it's not relevant to my investigation capabilities. We're interested in real-time. I do know folks who use the logging directly. Typically, those are used in detonation chamber style scenarios where they say, hey, I'm going to turn on 16 providers and then I'm going to launch this malware and see what it does and see what we pick up in ETW. That's fine, right? Because that's a one-off, but we're talking about endpoint protection and covering a server or a laptop or a machine that's running under somebody's desk, and you don't want them coming back to you and saying, hey, it's running slow. So what solutions do we have available, right, for real time? Well, you can do Win32, right? It's kind of cumbersome and inflexible if you know how to program in old school C Win32 style. It's programmed like it's 1992, 27 arguments for your functions, etc. There's system.diagnostics.eventing. That's available in the base class library of .NET, and it's a reasonable way to start out if you're just playing with the data in a programmatic fashion. But at scale, for us, we found it unreliable and to have poor performance, both CPU and memory, right? It creates an object for every event you get. Well, if you're listening to something that can generate 15 gigabytes worth of data in 30 minutes, you're probably going to generate a lot of events, event objects. Finally, there's trace event. This is not an exhaustive list, by the way. It's just a list that I know of. Trace event is also managed code. It's open source by Microsoft, but it has poor performance characteristics with memory, and I've heard from friends that it's not so great when you're talking about CPU either. So these are all problematic in one way or another. So that brings us to CRABS ETW. CRABS ETW was built by my team. It's a managed and a native API, so you've got a .NET API and a modern C++ one. It's meant to be flexible and intuitive, right? It looks like a .NET API. It makes sense in that respect, and it's very modern C++ for people who know C++. We built it for performance and scale, right? It's built for Office 365. So when I say that, what I mean is over 500,000 endpoints. In just the production environment of SharePoint Online alone, we're pulling in 12 to 15 terabytes of data a day, and that's after filtering, by the way. And probably processing somewhere in the 750 billion events across the environment realm, something like that, after filtering. And so this library is available now already, and I'll have a link at the end for how to get to it. It's compatible with Win 7 and above and Windows 2008 R2 and above. If you're below that, please move forward. Like at least Win 7, but preferably Win 10. All right. So it's example time. I'm not going to do any live coding, which actually that's kind of a lie because I got something fun to show y'all later. But this main part, it's going to be C#. It's code. I've realized that that's not necessarily what everyone wants. I happen to be a software engineer, and so when I look at problems, all I think of is how do I beat it with code, whereas I know folks sometimes are looking for tools, so bear with me, I've got a tool later to show you. The examples I'm going to show you are actual detections we use today in Office 365. They're in moderately simplified form, but they are legitimate ones that are used today in our agent. Let's see. So let's start with DNS lookup. This example lets us get every DNS lookup that goes through the core Windows resolver on the operating system in real time. If you use your own custom resolver like Chrome did for a period, it is not faster, or it does not capture it rather. And so starting at the top and moving down, we've got next to number 1 there, we're going to create a filter. And this filter is looking for event 3018 and event 3020. And that's a cache lookup for DNS or a live lookup. And then we're going to make a filter handler. And the filter handler is going to pull out 2 properties off that event record. It's going to pull out the query name and it's going to pull out the query results. Query name is the domain name that was queried for, and query results is what came back from the DNS server. And then that last line, we're just going to print it out so you can see it. Number 3, we're going to create a subscription to the provider Microsoft-Windows-DNS client. And we're going to add the filter to it. And then we're going to make our trace and enable the provider on that trace. Then we call start. Can you read that at all? That looks illegible. Is that legible even in the least? All right, that sucks. That's a cool slide. So this is a whole bunch of resolutions, responses from, what is it? Navigating to NewYorkTimes.com in Edge, in the Microsoft Edge. And so what you would see here, if you had the slides in front of you, is a bunch of A record resolutions, some CNAME record resolutions, and a couple of IPv6 addresses. And so these are all coming in real time. I'm not aware of a way to get the DNS resolutions that are coming through the system in real time in any other way. So if you know of a way, I'd love to talk. I'm hoping that the rest of my examples are legible. If not, that will be sad. So that now we're going to talk about PowerShell DLL DLL loading. This happens when an attacker ends up loading PowerShell in something you're not expecting. Usually it's system.management.dll or management.automation.dll loaded into something like winlogon.exe or maybe explorer.exe. So up there at the top, we're going to look for event ID 5. That's DLL load. And we're going to look for the image name property and have whether or not it contains system.management.automation. Again, we're going to set up a filter callback. We're going to pull out the process that did it, the PID. We're going to pull out the process name by asking the process class in .NET to get it for us. It's not available on the event, unfortunately. We're going to pull out the image name, and then we're going to print out that data. So, let's see. 3 is the same as it was before. 4 is the same. Nothing special there. We're just turning on provider, turning on the trace, starting it. Also illegible. How unfortunate. So up top is supposed to be a snapshot of PS Attack, which is a third-party tool by Jared Haight. And he loads system.management.automation.dll into a different process than PowerShell. And so what I've done at the top is what you would see is I said, hey, get me the current process and tell me what its process ID is and the process name. And on the bottom is the demo running. And what it shows is PS Attack loaded system.management.automation.dll from this path with this PID. And so it actually shows it doing it 4 times. The loader is weird. This is an interesting detection, at least from the standpoint of most of the time, system.management.automation is not going to get loaded into just arbitrary processes. You don't see that happen very often. In our environment, we see it in two other processes besides PowerShell.exe and wsum-prophost, and they're legitimate in those cases. But everything else is not legitimate. You can imagine also building a detection like this, like, hey, I want to look and see if mscorelib.dll, which is the core.net library, gets loaded into winlogon. Right? You don't expect winlogon.exe, which is a core Windows property, to do that. This is PowerShell execution, or rather, this is an example for capturing PowerShell execution. So every single method, unobfuscated, getting pulled out in real time. So if you've seen Daniel Bohannon's invoke obfuscation talk, he talks about doing all these interesting things with backticking and spaces and chunking and breaking up these different strings and slamming them all together and executing them. None of that matters in this case. Because at the end of the day, the weirdly obfuscated invoke expression still turns into invoke expression coming through as event 7937. So up at the top again, we'll build a filter, pull out event 7937. We're looking for things also that have a payload where the started string is contained in there. The filter callback that gets set up is going to have a, we're going to pull the context info out, and the context info is that property that has that big block of well-formatted code. 3 and 4, exactly the same as before. I'm assuming you won't be able to read this, which you cannot. The top is PS attack again. I have a little script that has a fake invoke Mimikatz in it. And what I've done is I've run the script called foo.ps1. On the bottom, you get that context info block I showed you at the beginning, except this time it says the host name is PS attack, and it says the host application is C user zbrown psattack.exe, and the command name is invoke Mimikatz, and the script name is the path to the script to foo.ps1, and then the user is my user. Finally, we're going to talk about thread injection a little bit. So thread injection is a thing that happens legitimately on Windows, but there are ways to kind of look for illegitimate uses of thread injection. It's a heuristic detection. We'll talk about detection types a little bit later and go into detail on that point. At the top, we're going to look for event ID 3. That's creating a thread. Here, this is a little more complex filter handler. We're going to pull out the source PID, pull out the target PID, and then we're going to check if the source and target are not the same, right? Because the event that's generated and the API that's used for creating a thread is the same regardless of whether you're in creating a thread in your own process or creating a thread in another process. It's the same API. And then there's a check I'm not doing here that I really should be doing, but there's not a brief way to show it in a slide, and it's whether or not the parent PID is of the target process is the same as the source. And that just means, hey, you know, when you created that thread, it might actually have been the initial thread for the child process. 3 and 4, exactly the same. Not going to go over it. That's actually sort of legible, at least. So what you see there, those highlighted lines in yellow are the ones I think are interesting, because I said this is a heuristic detection. And so the source PID here is 4956 injecting into 5108 with a thread ID of 4276. Those other ones are source PID 4 injecting into something else. Well, source PID 4 would be the system or kernel process, and that happens all the time. And so other legitimate uses of thread injection might be COM, might be the perf counters, querying perf counters. And there's something else I'm forgetting right now. So, but Zach, I'm not a developer, right? So I have a PowerShell demo. I didn't have this when I gave this talk at GrrCON, but I've been working feverishly to try to show people that you can do this with PowerShell as well. So bear with me. We'll see if you can even read what I'm showing, and if you can't, we'll just skip it and we'll go straight to something else, and folks who want to see it can find me later. Let's see. I want to mirror the displays and go here. Are you legible? Sort of legible. Is that fairly readable for folks? Okay, cool. Yeah. Cool. All right. PowerShell. So PowerCrabs ETW is my little wrapper around that Crabs ETW library I've been talking about. It is effectively meant to be, I don't like to use the word dumbed down, but it's a simplified version of interacting with the Crabs ETW library. Crabs gives you a ton of ability to filter, and all the filtering happens in the native layer so that you're getting all these performance benefits and you're not creating managed objects and keeping your memory footprint low. So first we're going to create a trace object. Nothing fancy there. We're going to create a provider, and that provider is going to listen to Microsoft Windows PowerShell. Now we're going to create a filter, and we're going to look for that event I've been talking about, 7937. And then we're going to set the callback filter for the provider. And then we're going to set that provider on the trace. Cool. So I'll clear this out real quick. And we're going to start listening. So what you hopefully can see there is at the top, command name like invoke Mimikatz. So now we're going to do bad PowerShell. Cool. Invoke all the Mimikatz, etc. And hey, look. So now you get a well-formatted block that shows you that PowerShell.exe was the one who ran it. If I had used PS attack instead, which I'm not brave enough to do that in a live demo, you see the invoke Mimikatz, the users there started, and this is the stopped command because we're picking up both in this particular instance. So that's at least that demo worked, and you could actually read it. So let's do the same thing, but now let's show WMI. Cool. Same thing, importing PowerCrabs. We're going to create a new trace. We're going to create a new ETW user provider, except this time for Microsoft-Windows-WMI activity, or dash activity. Create a filter for event ID 11. That's WMI activity that occurred. We're going to set an ETW callback on that. Again, same thing as before. Set the ETW user provider. Clear the screen a little bit, and then we're going to start it. And we're going to look for Win32 process create, right? Because you can use WMI to create a new process if you want to. So, WMI. Cool. So we created something with event ID, or with process ID 7420. And hey, look, we got a something that made it through the filter that we had on the pipeline. And so right here you see start IBEM WBEM services exec method Win32 process create. And so unfortunately you don't get necessarily the content of what was started, but I believe you get the process ID for the thing that was created out of there. And so you can imagine pulling that, hey look, we popped calc, we own the box, etc. So that concludes the two little short demos I've got for that. I'm glad I got to show you something that you could actually read. Where is it? This. Presenter view. Cool. Oops. All right. So let's go back to the forensic wish list that we were talking about. What DNS lookups did it perform? Well, you can use the Microsoft Windows DNS client provider for it. What IP addresses did it connect to? How much data was transmitted? Is it beaconing? You can use Microsoft Windows kernel network for that. What DLLs did it load? Did it create any threads in other processes? Microsoft Windows kernel process gives you that data. WMI operations, that's Microsoft-Windows-WMI, and there's also Microsoft Windows WMI activity. I didn't add that to the slide, that was my mistake. And then of course PowerShell, Microsoft-Windows-PowerShell. Keep in mind that these are the ingredients for building your detections. The demos I showed you are more the recipes. You'll have to figure out how to tweak those into your own if you have a dev team. If you don't, which I understand that some people don't, I'm trying to build out some tooling to make this easier for folks to do it who don't have a full-blown dev team to build out an agent of their own. So let's go back to bad.exe, right? Let's imagine, let's go revisit what we might have seen if we'd had ETW logging. So in this case, we got our process start. Nothing fancy there, but hey, we saw it load PowerShell. the PowerShell DLL. So you can imagine this is like what I was talking about. You see it load system.management.automation.dll. Nothing fancy there. We've already talked a little bit about the data. In this case, it's event ID 5 for the DLL load. This is, again, a heuristic detection. It's not a detection that you can necessarily just blast everywhere and expect it to work 100%, but it should have a pretty low false positive rate, in my experience. Obfuscated PowerShell. So after we saw the DLL get loaded, we saw it run some weird PowerShell. And I'm not talking about the obfuscated PowerShell where you inject all the weird backticks into the invoke command call. This is, I named my command something stupid, like ASDF1234, so that you can't figure out what I'm doing. So instead of calling it invoke Mimikatz, it's invoke ASDF1234. The interesting thing about that is you could apply something like Shannon entropy, which tells you how random a string looks, or you can apply bigram analysis to see whether or not it looks like English. Or actually, if you have the bigrams for German, or Swedish, or Finnish, or something like that, you can do bigram analysis that way as well. That's a statistical approach we actually use in our service to figure out when somebody's doing something weird like this. After that weird obfuscated DNS was invoked, we ended up having a suspicious domain lookup. And so that's using, again, the Microsoft Windows DNS client provider. There's two that I've already talked about, the cache lookup and the live lookup, but there's a third one actually that's really handy called, or with event ID 1016. It's for NX domain. And so that's something that's useful when you're trying to identify malware that is doing domain name generation and expecting a particular domain to have been created on Tuesday the 5th at 3 p.m. And so you'll get back an NX domain when that domain does not exist in the resolver, or in the resolution. So example data, machine, super server, queried fanciestbear.com, and the response was 1.2.3.4. Some notes about DNS lookup. I didn't talk about it earlier, but per process lookups are not available simply by collecting that data, because the core resolver actually is a single different process. So what you have to do is build a reverse DNS table where you store the IP address and the domain name that was resolved, and then when you collect your network data for what packets were sent out, you end up with a saying, hey, this process sent these many packets to this endpoint. What is that endpoint? Is that endpoint a DNS name I actually care about? Excuse me. Next we see data exfiltration by bad.exe. And so in this case, we're going to capture IPv4 send events and IPv6 events, send events. And so this comes from Microsoft Windows kernel network. I actually have an exfiltration example. All that example code that I showed earlier is available on GitHub already, and I'll have a link at the end for that as well. So you can imagine this ends up being a 248 megs exfiltrated to some known bad IP. Is the detection that you're looking for there. This is an instance where aggregation is going to be really important, and we'll talk a little bit about that later. Basically, when these send events come through ETW, the send events are per packet. So you don't just want to take that event and log it directly to a file or security event log, because it's going to be really, really noisy. So what we actually do is we aggregate it across 30-minute intervals. And then what we do is either when the process exits or when 30 minutes has elapsed, we'll log it. And so every process that's talked remotely to something, we'll do that with. Malicious PowerShell. This is just that 7937 event from the Microsoft Windows PowerShell provider that I was talking about. Works in any process that loads that system.management.automation.dll binary. In this case, we saw it call invoke reflective PE injection and then create remote thread. Well, then we saw remote thread injection, right? That's good, or bad, depending on how you think about that. Again, you saw the demo already, the demo code already, but effectively this is just, hey, PID1234 injected a thread into PID 5678 at 6:56 p.m. It's heuristic. But a nice thing that you can do with this sort of data, and it's what we do, is it actually triggers us to go scan the memory of the target process and see if there are executables running in memory space that does not have a thread or DLL directly mapped to it, because the way Windows memory works is when you load something like a DLL or an executable, it ends up being a mem mapped section or a mem image section. So what do? Do we forward everything to the SIM, turn on all 1100 providers? And I've kind of already hinted that the answer to that question is no, because it ends up looking like this. And so this is basically your SIM on unfiltered ETW, and that looks horrifying because the dog looks red in this picture up there. But I do love this picture because it does embody everything about a lab. My black lab, this is how he lives life. So event overload, right? ETW is for debugging. It was never meant to be used in the way we're using it today. But, you know, could your SIM handle every image load for every process started on every machine? Every packet sent across the network? What about every DNS resolution by any client on there? Probably not. Certainly not in my environment, where my smallest environment that's in production is 230,000 machines, roughly. So that's collecting a huge amount of data. So how do we reduce event volume, right? We got all this raw data that's floating around out here. We got our custom event handler, which we've actually kind of talked about when we were talking about those filter handlers. And so ideally what we're doing is we're generating this nice, like, compressed stream of higher fidelity, better distilled data and sending that to the SIM, which in turn is more useful for your SOC analysts or whoever ends up looking at your code or your alerts. So signals for reducing volume. I'm going to talk a little bit just like nomenclature-wise on how we think about solving the problem of signals and having too much data. This is not canonical in any sense. This is not even Microsoft canonical. It's just how we talk about it within Office 365. The list is not exhaustive, and if you think of one that I didn't talk about, I'd love to hear about it as well. So, number one is an oracle signal. Oracle is the general word that I use for source of truth or for deny lists and allow list, right? You have something, a system, a list, whatever, that tells you, yes, the IP is good, or no, the IP is bad, or yes, the command is good, no, the command is bad. So signals in your deny list are alertable, signals not in the allow list are alertable. And this is super handy way to think about this problem for us, because we spend so much time trying to codify what knowledge we have, and it often turns into an oracle. It turns into this source of truth. Oops. Aggregation is another actual type of signal, right? I mentioned it when we were talking about exfiltration, where you take all those packet, you know, every event represents a packet. Well, I don't need every event because I don't need to do packet inspection. What I need is how much data was transferred in a time window. So let the endpoint process take that, compress it down, and log it periodically for me to consume. Next, we've got heuristic. I've talked a little bit about that. That was the thread injection, right? It's not always bad, but sometimes it's bad. And so, you know, presence of signal may or may not be alertable. And in our case, the most common one that we're using it for is that PowerShell DLL loaded is an example, or the remote thread injection, and we get a lot of value out of going and doing that memory scan in process to see whether or not a process is doing something sketchy. Finally, there's statistic signals, right? A statistical model generating signals alertable. And so when I talk about this, I'm talking about things like the Shannon entropy or the bigram analysis I mentioned earlier. That's statistics. You also can look up a high-frequency trading algorithm and use that to look for regular activity. There's one that's actually publicly available, and we use that actually to look for C2s with a regular interval. But the other thing that this kind of covers as a bucket, and I intentionally am being vague about it, is machine learning and AI falls in this bucket, because typically those models are underpinned by statistical models. Oops. So here's a table with that data reapplied to the detections and kind of how that maps out for us. And so malicious PowerShell was a combination of aggregation and an oracle. And malicious PowerShell is aggregation because typically, like if you ran invoke Mimikatz, you actually end up running a whole bunch of really sketchy commands as a side effect of how that commandlet works. So we actually aggregate that down, compress it over 30 seconds, and say, hey, we don't need 2,000 events for this. We just need one event that represents the bad thing that happened. The oracle, obviously, is the deny list that I was talking about for PowerShell. Obfuscated PowerShell, that's the statistics model, data exfiltration, aggregation. And actually, we use the oracle because we don't really care about tracking the data that's moving within the network. We care when the data leaves the network and goes outside of the data center. So we're whitelisting all of our internal traffic. DNS lookups, that again is an oracle, right? You may have a passive DNS list that tells you what sketchy domains are out there. Threat injection, heuristic, and then the PowerShell DLL loaded is also a heuristic. As well as an oracle because you have a list, an allow list of processes allowed to do this. Right. We're going to talk about gotchas briefly. Don't worry, I'm getting close to the end. I know it's been a long couple of days. Not everything can be sunshine and rainbows, which is true of ETW as well. So for performance and reliability, CPU usage is directly correlated to event volume. It's almost always your network data. You're almost always not filtering enough of your network data. Like I said earlier, we filter all of our intranet traffic. We don't watch it at all. We only pay attention to when things cross the boundary and go outside the environment. And even then, sometimes we'll allow list certain endpoints. It's like, hey, this particular Azure endpoint that points to a traffic manager for this service, it gets so much data we'd never be able to see anything in there anyway. Events can be dropped if you don't pump fast enough. So ETW has a circular buffer in there, actually multiple circular buffers when it's running on the operating system. And so you pump events off the buffer, but if the buffer fills up and you get back around to the front, it just starts knocking off things from the oldest things out of there. So frequently what you want to do is you actually want to have really good filtering, and you want to return control of pumping those events as fast as possible. Also, ETW occasionally writes bad or missing data, or writes events with bad or missing data. So once in a while, we'll get a process start event, because we listen to process starts to correlate with the 4688s. And those will just have gobbledygook for the process path, or gobbledygook for the process name. It'll mean nothing. On the tampering side, which is actually the side that I'm more concerned with, trace sessions can be stopped by an administrator, right? And administrators can do anything they want. Trace sessions can be modified, so that's actually the scariest one in my opinion. Your agent is happily chugging along and it's listening to the PowerShell trace and the WMI trace and the networking trace, and then your malicious attacker comes by and he says, hey, I'm going to turn off all those traces. So you went from processing 100 events per second to all of a sudden I'm processing no events per second. The lesson to learn here is not, hey, we can't use ETW because it's got this tampering mechanism. The lesson is you need QoS. Like if you have an endpoint protection of some sort, you need to understand whether or not it's actually pumping the data you expect it to be pumping. Also, malicious software can write fake data to existing ETW providers, so it can pretend to be the PowerShell provider and write bad data there. Or fake data. In the bad data case, that one's scary because if you're doing any interesting parsing, you might crash the agent. I don't have a POC to share for this, but I know that it's possible. So what did we find, right? What did we find in SharePoint Online? What did we find in OneDrive? So how does the red team do? We found them doing WMI things, kind of that example I showed earlier with the process create. PowerShell command execution, so invoke Mimikatz, that sort of thing. PowerShell DL loaded in anomalous processes. They really, really liked loading PowerShell into winlogon.exe. New processes uploading to external endpoints. And beaconing processes, so C2 communication in this case. Well, that's kind of legible. Okay, good. So this is a graph we were able to build because of our networking data that we collect. The little gray nodes in there are processes, and the green squares are Microsoft-owned properties. The teal squares are Azure specifically properties, and the red squares are external. They're not bad, they're just external. And then those red arcs here, here, there, those are where we saw periodic activity. to the network, to that endpoint, whatever that endpoint might be. And so the interesting lesson here was we use the data to graph and see what sorts of things we're talking to what. One of the biggest problems that we have in this, or in any environment, I think is probably true for a lot of people, is when the developers go and they work on SharePoint Online, or they go work on OneDrive, or they go work on Exchange Online, they don't consult the security team and the security software engineers to find out, hey, we're going to go talk to this new endpoint. We usually find out by accident when it trips one of our detections and says, hey, we're suddenly uploading to this new weird Azure website that wasn't there before. And so being able to build these sorts of graphs and understand what things are going where and what's normal, and being able to drill down on that has been really handy for our team. It's a lot of recon we didn't have before. But will it scale, right? So I've been kind of making allusions to the numbers. These are the numbers from January 2017 after filtering. More than 100,000 machines, more than 7 terabytes of data per day, and more than 500 billion events across the environment. And in reality, this is actually, that number, it's more like 200,000 machines now, it's more like 14 terabytes of data now, and it's more like almost 1 trillion events per day. And that's all after filtering, all after aggregation, all after all those signals I've been talking about. And we're pulling all that data in. And so I'm hoping that this is like the problem of scale is evident from this slide. But I don't want you to get scared away from ETW just because of how much data it can generate. There are ways to pare it down, and there are ways to work with it. It takes some investment, but it's such a treasure trove of data that's available. And you don't have to install a kernel driver for it. You don't have to install some weird extra update pack or something like Emmet to get it. It's there. All right, wrap it up. I'm still talking somehow. How can you use it in your environment? So CRABS ETW, talked about it earlier. It's open source under MIT. You do whatever you want with it. I still have to figure out how to set up the proper legal thing so that if you want to contribute back to it, you sign the thing that says, yes, Microsoft owns the code, you don't own the code, but you get to use the code however you want to use the code. PowerShell Method Auditor is open source, and that is a project I wrote for Daniel Bohannon to play with PowerShell and how the 7937 event occurs. For those of you with the camera out, I've got the link. The very last slide has links, and they're short links. So what's next, right? PowerCRABS ETW, you guys are the first folks to actually see that in action. I've been working basically every night of the week for the last 3 weeks since I got back from Derby, trying to get it to work, much to my wife's chagrin. Eventually, I'd like to add Sigma and Yara rules to it so that you can just say, hey, I've got this Yara rule, look for this event that looks like this, and then we'll set up the filter so that you get the native filtering benefit there still. And I'd like to also create a trace process where you say, hey, I've got this sketchy executable, here's the path to it, turn on all the interesting tracing, run it, and then when it's done executing, turn off the ETW traces, and here's a file, a CSV, that has all that data, or a bunch of JSON, right? FlatC API, that's kind of my own pet project, but it's specifically, I've had people ask if there's a way to use CRABS ETW with Go or Python, and right now, because it's modern C++, it's really hard to integrate, so I'm trying to get that to a point where people can integrate that themselves. These aren't done yet, but I'd love your feedback if one of these is really something you want to see, because it indicates whether or not I spend more time on it. Finally, that's the end. Those are the promised links. You can find me on Twitter at Zach Brown. I don't tweet that often, but when I do, I like to think that it's kind of useful. GitHub.com/Zach Brown. That's me just puttering around in my code. You'll find weird little programming projects in there. And then that first link, aka.ms/ETW, that's for CRABS ETW repo. aka.ms/ETW demo is for the code that was showed earlier, minus the PowerShell. aka.ms/PowerShell method auditor is that PowerShell method auditor I talked about. And then finally, the last one, aka.ms/message analyzer is the message analyzer link. I don't have a link yet for PowerCRABS ETW, but I will, it'll be open source in the next day or two as soon as I've got the code cleaned up. Any questions?
Are you aware of any emerging products that are utilizing this interface?
The question was, am I aware of any products using this? I can tell you, I'm not allowed to be specific, with the exception of Windows Defender ATP, which is new as of Windows Server 2016, and Windows 10. That's available. That's using ETW heavily underneath. In fact, we worked with that team to build that agent, or not to build the agent, but to help them design the agent. There are major companies in the bucket of, FireEye, CrowdStrike, Tanium, that sort of company that are using ETW to enhance their analytics. I'm being intentionally evasive there because I'm not sure whether or not I'm allowed to tell people specifically who. Yes. So we're literally calling open process, the open process API, and we're getting a memory read permission. And then we're looking for a couple of specific things. We've got a library that'll do this, and I'm working to go through the open source process. So if you kind of keep an eye on stuff in the next few months, hopefully I'll be able to open source that. It's kind of a lower level library, but it's pretty straightforward in how it works. It basically just goes and says, hey, I'm going to open that process. I'm going to scan the entire memory space, and I'm going to look for threads running where memory is not mapped to an executable on disk. And if it is, then I'm going to dump that whole section of memory. It was really, really fun to write, if that's any consolation. I'm an OS dork, so go figure. Any other questions? No? All right. Thank you.